Ashwin, this is Soham, and this is Ashish. And our presentation is on the paper CLEVRER. So CLEVRER is actually a data set, and in this paper we'll be using a mod called NSTR, which Soham will be explaining later. So the ability to recognize objects and reason about the motion of the objects is it lies on in the core of human human cognitive development. And even kids nowadays, they they group segments into based on the motion, and we use concepts like object permanence, solidity, and continuity to explain what is causing it and why it's going to happen and infer what might happen next. And also we use counterfactual situations to predict what might happen if this something something else that didn't happen right now, what that happened. So that's what they're trying to implement in this. So the CLEVR stands for Collision Events for Video Representation and Reasoning. It's a video data set for temporal and causal reasoning, and it works under a fully controlled environment. It includes 20,000 videos and 300,000 questions and answers. And so the dataset mainly follows two guidelines. The dataset mainly follows two guidelines. So the listed tasks should have logical reasoning in the causal and temporal domain, and it shouldn't consider more of visual scenes or language. So it should stay unbiased, or at least try showing minimal bias to the visual and language. The dataset has to work in a fully controlled environment so that in order to host the complex reasoning tasks and questions. So it includes, out of the 20,000 questions in the dataset, 10,000 of the questions are used for training, and then 5,000 of them are for validation, 5,000 are for testing. So the videos mainly describe motion and collisions of objects on a flat tabletop. They are associated with the ground truth motion tracer and histories of all objects and events. All videos in the dataset last for 5 seconds, and the videos are generated using a bullet physics engine. And then that's passed on to a rendering engine, which is Blender in this case. Okay, so this is the CLEVR dataset compared to other datasets. CLEVR has 4 main different type of questions, which is descriptive, explanatory, predictive, and counterfactual. You can see that other datasets have all these causal questions in them. So CLEVR mainly tries to improve the causal questioning part of the dataset. So there are mainly three shapes in the dataset, and 2 materials and 8 colors. So the shapes are cubes, sphere, and cylinder. The materials are metal and rubber, and the colors are gray, red, blue, green, bronze, and purple and yellow. All the objects are of the same size, so there is no vertical bouncing between objects. And as there are no duplicates in the objects, any 3 combination of any 3 attributes can be used to represent the object. And there are 3 main events in the dataset, which is enter, exit, and collision. And each of these events has a set number of participants. So for collision, it's two objects, and then one for entrance and one for exit. And all of this occur at the same time. So the collision pairs and motion trajectories are randomly chosen in this. There's repetitive collisions between objects, and the collision actually it starts by initializing a random object, which also has a second object which has a set position and velocity in such a way that it collides with the first object, and this is repeated to have more objects and collisions in the video. So, so if an object participates in an event for the first time, it can either be the cause of the object, or it may be a different event if the cause of the object occurs in the same object before the result event. And for example, here you can see the cylinder, like the sphere collides with the cube, which in turn collides with the cylinder. So here the cube jointly is the cause of the second collision. So in the video generation process, it mainly includes videos of objects collide with each other. For the physics part, there's bullet physics engine used, and then each of the videos are 7 seconds long and 25 frames per second. Yeah, so for first 5 seconds of the video is sent to the blender for rendering and rendering of the object and object motion and collision, and the rest of the 2 seconds are used if there are any other predictions to be made. So there are mainly 4 types of questions, as I mentioned earlier. So in explanatory, they ask whether, like for example, whether an object or event is responsive for another object. So in the first picture, you can see if like the cylinder, the gray cylinder is responsible for the movement of the second cylinder, which you can see in the second picture. So questions like that is what explanatory asks. Next. And in counterfactual, it comes up with hypothetical conditions. So this includes questions like without the gray cylinder, what would happen? Like, will there be a collision, or will there be another object or something like that? And in descriptive mainly includes questions like what kind of material is it, what kind of color is it, and there are many 5 parts under descriptive. So this includes the number of objects in the video frame, the number of does the object exist or not, the material type, and also the shape of the object. And predictive questions, it tests the model's capability to predict possible occurrences in the future. So these are the different types of questions these are subtypes under descriptive questions. So it's the number of objects, does the object exist or not, with the material, shape, and color. So Ashish will be doing the next one.
Okay, so now that we understand a little bit about the CLEVRER data set, now we can take the models that have been used on the previous data sets that were on the slides before, and we can use those models and see how they perform on this new data set. So the authors have categorized the models into 3 categories. You have language-only models, models for video question answering, and then models for compositional visual reasoning. I'll spend a little bit of time to just briefly go through what models they were using. So in the language-only models, this you want to consider as being kind of like your baseline, your control. It's very, very straightforward. The Q-type random is just a uniform distribution over all the answer choices, and if it's a multiple choice, it just picks one. And then the Q-type frequent, it just chooses the most frequent answer that shows up in the training data, whatever it is. Just to apply like a little bit of technique, I guess, they also use an LSTM, which is pre-trained on the Google News corpus. And then they use that to encode the input questions. And then they use an MLP to create a distribution for the answers, to predict answers. In the video question answering, they use a CNN plus an MLP. So the CNN just is it grabs the features out of the video parser. And then the MLP, again, just creates a prediction over the answer choices. And then they do the same architecture, but instead of doing the MLP, they do an LSTM for prediction. And there will be a little bit more detail that we'll go into on that in someone's part. Next slide. Oh, yeah. Also in the video question answering section, the previous state-of-the-art model was TDQA. And in this one, that's a multi-stream end-to-end neural model. And what they were doing, what the authors did is, in order to make the results comparable to the previous data sets. They did a little bit of adjustment so that they could take into account the new features that are being added into this data set. So whenever you see this plus on the model, and there's going to be a results chapter slide that we're going to go to, what that really means is that they just took attribute-aware object-centric features from the video parser. So that's what the plus means. And they also used another model that performed well, not just on the previous data set, which was CLEVRER, which is what this is an extension of. They also took they used this model that's called memory that performed really well on other data sets, not just CLEVR. And it incorporates a heterogeneous memory with modal attention work. And this one is like what I would call the generalized model for video question answer. Next slide. The next section, the third section, is compositional visual reasoning. So just to remind you what CLEVR was good at, they introduced a new route in compositional visual reasoning by emphasizing complexity and compositionality in logic and visual context. And so one of the models that tended to perform well in this category is the IEP model, which employs neural program execution for visual reasoning on pictures. And then to make it a little bit more comparable, they took the program-based video reasoning, they took the primitives from the program and they replaced them with the CLEVR primitives. And that's really all they did. And then they used an LSTM, a convolutional LSTM again on the answer choice. And the one that really performed really well was MAC in the MAC. And this includes a shared attention mechanism on both of the picture features, both the picture feature map and the question, resulting in very high performance on CLEVR. And then what they did was to make it a little bit more comparable with this new data set, the CLEVR data set. They applied a temporal attention unit across the video frames. And then they also, in addition, they did another version, which is MAPV+. And the MAPV+ takes that attribute-aware object-centered feature set from features from the video parser and put it in there. So that's all three combined. So this is the output. This is the results of the previous kind of like well-recognized good models for this type of application. So again, the top section is kind of like your controls, your baseline. The middle section is your video question and answer. And then this bottom section is your compositional visual reasoning. And so as you what the few things that you should maybe take away from this is you can see that there's a performance decrease as soon as you go from descriptive to any of the causal relationships overall. And then in particular, you can see a huge performance decrease when you go from the per option causal relationships to the per question causal relationships. And hang on to that, I'll explain that in a little bit more detail in a second. But I also want to point out that you should see a improvement when you add in the plus, which was that attribute-aware object-centered features. When you add in, you do see a performance increase on the causal relationships. So that is actually pretty interesting to know. I'm not saying it's going to be, obviously these are not great numbers, but you can see that there is a meaningful improvement. There is some impact. And so really what we want to understand is what's going on here. Why is it that we're not really getting really good results, and what is the underlying cause of that? So next slide, please. For descriptive, so the way to understand this is to first know what they're actually measuring. So for descriptive questions, it's quite simple. It's just comparing the output answer to ground truth. But for the multiple choice questions, what they're doing is on per option accuracy measures, they're measuring the model accuracy on the individual answer choices. Like, does it say that this is an answer choice or not? So that's why you were seeing a 50-50 output on the control. But when you're looking at accuracy measures on whether or not the model got the whole question right, meaning did the model only select right answers, did not select wrong answers, and selected all of the answers correctly. So meeting all of that criteria. And that's where we saw the massive drop in performance. And so really we want to hone in a little bit on that one. Why is there a big performance drop on the previous existing models? So descriptive questions require strong perception and logic operations on both visual and language signals. So video QA models, they fail on this task because they have a poor capacity to handle compositionality in the question logic and visual context. So on the other hand, the models that were designed for compositional reasoning are able to achieve more complete competitive performance. So that was the bottom third section of the results chart. Those models tended to perform better. So what? Oh yeah, and then the compositional reasoning models that they perform well on descriptive questions like MAC, and there was also the TBD-net, which I didn't quite understand. I have to admit all the way what the major difference was between TBD-net and MAC. It was just like lots of details, to be honest. There's a lot of models, but I'm going to give you the best understanding I can, and just caveat it that it may not be fully correct. But TBD-net, I believe, is applying an attention map over just the video component of the features, whereas I believe MAC is applying attention map over the visual portion and also the questions. That's my understanding. I hope it's somewhat right. Okay. I'm sorry, could you go back one more time? Here. Yes. And so just to reiterate, as we are able to see, the TBQA plus model and the MAC-V plus model demonstrated that there is a value to including object-aware features in causal relationships. And we were able to see that because the MAC-V plus results did achieve better performance than just the MAC-V. So we were able to determine that. And that was universal. It was across all the categories. So to summarize, what are the conclusions that we can draw from the data set? The authors state that object-centric representations are essential for a causal reasoning task. I think we can agree. And then they also propose that all baseline models lack a component to explicitly model the dynamics of the objects and the causal relations between the collision events. So what the authors are proposing here is that as a result, the combination of object-centric representation with dynamics modeling indicates a potential solution for the causal relationship. So maybe if we can model the dynamics, we might get improvement in the model accuracy. And so Soham is going to talk about what the authors propose, what architecture the authors propose.